So more good news, 14.3 is about double integrals in polar coordinates. So double integrals aren't so bad, and they're even less trouble when you're dealing with them in polar. Um, the PowerPoint, again, is not the best PowerPoint that's out on the market. The big ideas that you want to remember from in here is that x is our cos and y is our sine. Of course, r squared is x squared plus y squared. Tangent theta, you don't see a whole lot, but that is a big idea when you're dealing with polar coordinates. The graphs are kind of reviewed quickly so that you can kind of remember, the cardioid and what that equation looks like, and that you're talking about circles. It's really just r equaling a number, and of course you can restrict that domain so you have sections of the circles. It doesn't do a very good job, though, I think, of convincing you of the swap in the formula from the double integral of f of x, y, dA over to the r cos, r sine, which makes sense, but then the dA becomes r dr d theta. And it kind of feels like there's an extra r floating around in there. And so even though they have some pictures that they try to describe what is going on, I think that this one that I stole from mathforum, I believe, .org, does a little bit of a better job of explaining why now that change in the area is represented by r dr d theta. So if you're opening up two angles, I have this black angle opening up here. I'll make him theta 1, and then of course the red, he'll be theta 2. And so that this little wedge that's created is delta theta, right? There's that little extra sweeping motion to create that extra angle. So when you're starting to find the area, of course, you start creating partitions. And so you stop somewhere, and that's going to be r because you've extended a radius. And then you have to make another section. So you go a little bit more. So r plus a little bit more is going to be our dr in here. And so this part, I think, also makes sense. You go, well, r plus a little bit more, and our delta will be our delta r. This part right here, though, if you want to know, well, what is this length that looks quite straight, is not really straight, right? Because we're in polar. And so arc length is r times theta. Except it's not really theta. It's not all the way back to here. It's only this little section in here, which is the delta theta, that extra sweep. And so instead of r times theta, it's this section would be, that length would be found by r times delta theta. And of course, to find the area of that little partition is going to be the r delta theta times the dr. And that's where the kind of mysterious extra r comes from when you're doing your swaps. And so the r dr d theta is kind of your starting point, much like the dx dy is your starting point for the other one. So that r will always pop in there. When they give you equations to solve, like just solve me's that are already in polar form, it will just be the r dr d theta. And during the changeovers, if we have ones with x's and y's, which we will in a little bit, that's when extra pieces of the integration will come in. Right? So for this one, you would just kind of start integrating the way that you always did and kind of look at it like this, right? So we're going to integrate with respect to r. So that this is going to now become r squared over 2 from 0 to 7 cos of d theta. Plug in my 0 and my 7 cos, and of course the zeros zero out, and so I have 49 cos squared over 2. I'm going to stick the 2 out here. Cos squared d theta. And one thing that will pop up a lot when you're dealing with polar is power reducing formulas. And so you'll have to dig those up like I did over here. And cos squared, I'm going to swap that guy out, and I'm going to put in 1 cos double theta over 2 in. And so I got 49 over 2 1 plus cos 2 theta over 2 d theta. And we can start to kind of clean this guy up a little bit. I'm going to scoot him this way. First, I am going to split this guy up. So I got 49 over 4, right? Because if you kind of multiply that, and then I'll have the times the 1 plus cos, ooh, goodness, 1 plus cos 2 theta, d theta. And we can kind of pull him out, but I'm going to do that kind of all at once. So I would have 49 over 4 from 0 to pi, the 1, and then I have this plus cos 2 theta. And so this is going to be my u. And so du is just 2 d theta. So I'll need a 2 in and a half out. And so I'm going to put, maybe I will write it because it's already pretty messy. There we go. So 2 in, a half out. Okay. And now we'll have 49 over 4. Now this is going to just become theta. So pi minus 0 is just going to be pi. Plus, this becomes cos u. So how about sine u? And I have 1/2 times the sine of 2 theta, and this is going from 0 to 2 pi, all of which is useless, right? Because 0 and 2 pi, if I'm talking about sine, I still have a 0. And so all of that for 49 pi over 4. It's not too terrible, although that probably didn't seem like it was very nice. Here's another one. I got r squared sine cos dr d theta. 0 to 4 and 0 to pi over 6. Let's go ahead and start with our integration with respect to r. So now I got r cubed over 3 sine theta cos theta, 0 to 4 d theta, yes. So if I plug in a 4, that's all I'm going to be left with, since the 0 will wipe everybody else out. 64 over 3 sine and cos. That's convenient. And so that I have, let's make this u and this du, right? So that it would be this sine of theta. And if I take as u, then du is cos of theta d theta. So all of this will come out, and I just have sine of u. So 64 over 3 times, we got a u squared over 2. I'm not even going to write it like that. I'll say sine squared theta over 2 from 0 to pi over 6. So of course 0, not helpful. Pi over 6, sine of pi over 6 is a half. Squared is a fourth. Divided by 2 will give me an eighth. All of that for an 8 over 3. So pretty quick. Right, setting them up is probably the worst part. So there's a couple of swaps. X squared plus y squared. So we know that right away is an r squared. Now it already has an r in here. And so this is actually going to be r cubed in there. And then this piece right here, if this is equal to y is equal to 64 minus x squared. If you square both sides, we'll get 64 minus x squared. And when he comes over, of course, I got x squared plus y squared is equal to 64. X squared plus y squared is r squared. And so our r is going to be an 8. And d theta, let's see, we're going from negative 8 to the positive 8. So it would just be from 0 to pi, since we're not going all the way around. Oh, they want us to do it. Well, I guess we're just going to have to scoot this guy down a little bit. Okay. So now we'll have 0 to pi. R to the 4 over 4 from 0 to 8, d theta. 8 to the 4th is whatever 64 squared is. So I'm just going to say 64 squared at the moment of d theta, which will wind up with a 64 squared theta from 0 to pi. And once we figure out what 64 squared is, it will be multiplied times pi. So pretty big. This one's a little trickier. We have the xy. So that's r cos and r sine plus another r. So, well, or multiplied by another r. So r cubed cos sine. Now this piece here is what we're going to need to clean up. So y is equal to 6x minus x squared. And my first thought was to move everybody over and complete the square, which may work, but it's going to be easier to do my swap for my polars right here. So 1r sine. This is going to be 6r cos minus r squared cos squared. And what will happen is when I square both sides, I get r squared sine squared. 6r cos minus r squared cos squared. And of course, when he comes over here, I get an r squared sine squared plus an r squared cos squared. Factor out the r squared, and you're going to be left with a 1 because of sine squared plus cosine squared equal to 6r cos theta. I lost my theta on the other one up there. And if I divide off an r from both sides, we get r, right? So r is equal to 6 cos theta, which will go right in here. 6 cos theta from 0 to 6 for my y. So we are stopping at pi over 2. And we need to do this one too. More big numbers. I guess I'm going to have to open up my calculator. So let's see. R to the 4th over 4 again. Cos theta sine theta from 0 to 6 cos theta. D theta. Okay. Let me get my calculator. So we have 6 to the 4th, which is going to be a 1296. Yeah, 1296. Cos to the 4th, theta over 4. Then another cos, so I'm going to do this right now. Make him a 5th sine theta d theta. 1296 divided by 4, 324. Let's pull him out. Ooh. And if u is cos, du is negative sine d theta, so I will need a negative in and a negative out. And he becomes u to the 5th du. I know these technically these should change, but we'll be fast, so we won't worry about it. 324, this is now u to the 6 over a 6. And we're going to take our u to the 6. Well, it's not really u, right? It's actually cos to the 6th. 0 to pi over 2. Pi over 2 for cosine is 0. Cosine of 0 is a 1, but it's a minus, right? So we'll get negative, well, minus the 1 to the 6, so minus 1. And then minus times the negative, so back to the plus of 324 over 6. Is that a nice number? Yes, 54. So that one was nice too. Okay, write this one first. Octant, I believe it's pronounced. So, right, we got our quads. And then, of course, he's 1, 2, 3, 4. But if we're going to talk about a poorly drawn z-axis that we'll have now 4 sections on the top and 4 sections on the bottom. So we're looking at this is basically where our only the positive x, y, and z's, right? So only up in that first, like the equivalent of the first quadrant, but now with the z. Okay. Z is x times y, so actually it looks exactly like the last one did, right? R cos times R sine times another R. And then we are going from 0 to 1 for my radius. And it looks like, oh, well, first octant, it will be 2 pi over 2 again. And since we basically just did this one on the other side, I'm going to spare you the watching me do it again and look at the last one because he's a little bit more interesting. So we got our 2 cos 2 theta, and we want to find the area of the shaded region. And there's a couple of different ways that you could do this. I think the easiest way would probably to just find this one piece from the 0 to here of that shaded region. And let me see if I can shade it a little bit better. Well, I wouldn't say that's better, but it is. And we have our R. And so what we need to find is what angle we're going to be opening up till here. So I have R, dr, d theta. And we're going to go from the 0 to the 2 cos 2 theta. And so there's a couple of different ways that you can go about doing this. I pulled up the calculator because that's going to be the probably the fastest way to kind of give you an idea of what happens. And I did a zoom trig so I can get a little bit of a better picture than when it's in the other form. And when you kind of start to hop around, so you can see that we're at theta being 0, and as it gets bigger, it's going to work its way over. And it doesn't really ever quite hit the y exactly 0, but it gets pretty close. And now, of course, that's not in the form that we're really going to want to use it in, but you can then kind of work backwards to figure out, well, what is that as far as an angle? And so you have a pi over 4 there. And after a while, when you start to look at them a whole lot, you get used to them. But the other thing that you could do, which is would be a little bit longer sometimes, is to actually say, well, when is this going to hit 0 again? When, because it goes like this. Oh, actually, you didn't see a graph, so I'm gonna hit the graph. Let me change it so that it will show you the switch. Right, so it starts there, goes through, right? And so you can see how the order that it goes. So it starts here, comes, wraps around like this, right? So that it will finish up there. So when does it hit through this origin? Well, a bunch of times, right? So 2 cos 2 theta, when are you going to be a 0? Divide off the 2, say inverse cos, and I'll get 2 theta is now equal to either, let's see, cos is 0 at pi over 2 and at 3 pi over 2. And I'll have to divide off that 2, and when you have that speed up or slow down, we'll have theta being pi over 4 plus, well, it was a 2k pi, so now it would just be k pi. That's our first starter. And then the other one would be 3 pi over now 4 plus what was a 2 pi k, so now just pi k. And then you start letting k's equal, 0, 1, 2, 3, like that. And you can go back negative too if you wanted to find this side down here. And when you start plugging these guys in, you'll see pretty fast that my first round of solutions, of course, is the pi over 4 and the 3 pi over 4. And then every time I plug in a 1, 2, 3, 4, these guys are going to get a lot bigger. It hit this at the first one, the smallest one, which turns out to be pi over 4. So 0 to pi over 4, and the rest is a lot easier, right? So if I'm going to talk about integrating this with respect to the r, he becomes r squared over 2. Of course, go from 0 to 2 cos 2 theta d theta. Plug this in and we get 0 to pi over 4. Let's see, he is 4 cos squared 2 theta over 2 d theta. So I'll have a 2 that I'm going to stick out here. And now we need our power reducing, which is, let's see if I can remember, 1 plus cos 2 times the theta, but 2 times what you already have, so that's going to be a 4 over 2. Pull the 2 out so that the 1, now he's a 1. 0 to pi over 4 d theta. This would, well, this is, of course, going to just become a theta. He is going to need a 4. So I'll have 0 pi over 4 of just the 1 d theta plus 0 to pi over 4. He's going to be a cos of my u. So I need a 4 in and a 4th out. So that I have cos u. So now sine. So how about theta plus, yep, 1/4 sine 4 theta from 0 to pi over 4. I don't know, my brain skipped for a minute there. Let's see. Plug in the 0, so no excitement there. But if I plug in the 4th, I get pi over 4 plus that is sine of pi, which is a 0. Oh, yay. So pi over 4. But, scrolly, this is pi over 4. I have 1, 2, 3, 4, 5, 6, 7, 8 of these guys. So really, you got to say times 8. All of that for 2 pi. That was a lot of work for something that was just a 2 pi. It's a little depressing. So it's certainly other ways that you probably could have went through and done that. I think that's probably the most straightforward way, because this will have a jump, but you could find this one and then find this one, but it's going to be symmetric, so no real need. I'm going to send you this blank and filled out with all my lovely scribbles, the PowerPoint, and then I saw this guy. They had a couple other examples, so I'll send you the link that I just kind of saw online. It does have questions at the end. It doesn't have a key or anything like that, but something else to look at in a written form.